Good evening. I'm Ron Poling. I'm the head of the School of Physics and Astronomy in the College of Science and Engineering here at the University of Minnesota, and it's my great pleasure to welcome you to this 12th Irving and Edith Misel Family Lecture in Theoretical Physics. Mr. and Mrs. Misel endowed this lecture series in honor of their lifelong friendship with William and Bianca Fine, the benefactors of the William I. Fine Theoretical Physics Institute, or FTPI. The FTPI is truly one of the gems of the university. For more than 30 years, no, not more than 30 years, almost 30 years, don't get ahead of ourselves, it has brought to our campus faculty and visitors that include some of the most creative scientific thinkers in the world. For more than a decade of that time, the Misel Lecture has provided an annual opportunity to celebrate physics with lectures from eminent scientists who are working on some of the most profound questions of the structure and evolution of the universe and the nature and behavior of matter and energy in all their forms. The FTPI and the Misel Lecture demonstrate the value of having a great research university in our community. Events like this one allow us to welcome friends from around the Twin Cities area to sample the mystery and the excitement of questions that are generated by humanity's most basic curiosities. Some of those questions propel the brightest and the most energetic among the young people around us to seek out careers, to seek out opportunities in studying science. And some of those go into physics, but many more of them take that excitement and explore other areas of science or engineering or technology. We're very excited that some of the people who have had the experience of attending these lectures have gone on to become students in our programs and in programs elsewhere, and we look forward to some of tonight's audience members coming to study with us and do research with us at some time in the future. We, of course, would not be able to have events like this without the generous support of people like Mr. and Mrs. Misel. Please join me in recognizing the Misel family for their support of theoretical physics at the University of Minnesota. There they are. Thank you. And now I'd like to introduce Professor Keith Olive, the director of the Fine Theoretical Physics Institute, to introduce tonight's lecturer.
Good evening and welcome to the Misel Lecture in Theoretical Physics. So what's in a number? Let me tell you what I mean by that. You might have heard that the universe is expanding, and if you haven't, you'll probably hear about it in tonight's lecture. There's a number that characterizes how fast it's expanding, and that number is usually associated with a name which is Edwin Hubble. The fact that the universe is expanding, we've known that now for about 100 years or so. It actually has a funny history because about 100 years ago, this was a surprise, a little bit of a shock to Einstein, because he found in his theory of general relativity that his solutions had the universe either expanding or contracting. And to his dismay, he thought this was a huge problem because he wasn't aware of the observations. There actually existed observations before Hubble by an astronomer named Vesto Slipher, who found that there were distant objects receding. So Einstein thought, well, how do I fix the theory? And he added something that was a constant of integration, if you know from calculus. We now call it the cosmological constant, which I think you'll also hear a little bit about tonight. And by doing so, he could get it so that the theory predicted that the universe wasn't expanding, and we call it the Einstein static universe. And despite the fact that there were some observations that the universe was expanding, it wasn't until several years later that Hubble's work made it apparent that the universe was in fact expanding. And then Einstein recognized, well, this was a sort of an embarrassment that he added this constant. Of course, it's not clear that it was an embarrassment or really another stroke of genius, because now it seems that that constant's necessary because the universe is not only expanding but accelerating, and that constant might be what's responsible for that acceleration. Now, Hubble had the number way off. That number was 500. Don't worry about the units. Maybe you'll get the units a little bit later. But when I grew up, that is when I was a student, that number was either 50 or 100. That was it. It was 50 or it was 100, and one person said 50, another said 100, and yeah. As a theorist, I sided with the 50s, to be honest with you, because as a theorist, we knew the universe was flat. We got that one right. The universe had no cosmological constant. We got that one wrong. But without a cosmological constant in a flat universe, the number should be 50 or a little bit less than 50. So we sort of were a little bit more sympathetic with the 50s. In the 1990s, Professor Freedman was telling us, no, it's somewhere between 70 and 80. Now, this wasn't just because she was trying to be politically correct and get the number between the two. This was the number coming from hard research. And this came about through the study of what are called Cepheid variable stars, which she's very well known for, and I think she'll talk a little bit about tonight. These come about because you need to have a way of measuring distances in the universe. And that's, if you think about it, if you think about how far away a distant galaxy is, it's not very obvious how you determine that distance, right? You can't send a signal and then wait for it to come back. It's actually much more complicated than that, but it's very difficult to get a good handle on distances in the universe, as the universe is as large as it is. These Cepheid stars are variable stars. They pulsate, and there's a very tight relationship between their period of pulsation and their luminosity. And so you can measure that period, and you can measure the brightness, and if the brightness isn't what you think it should be, usually it's going to be dimmer. That tells you how far away it is, right? So if you think it's supposed to be 100 watts and you measure 25, well, then you know it's farther away than you thought. This was actually perfected. This method of measurement was perfected by Professor Freedman, and which led her to determine that the real number should be between 70 and 80 at that time. If we jump forward to the present day, there's still a fight about this number. But the fight is that it's either somewhere around 68 or 73, right around the number that she was predicting quite some time ago. And so we're very happy to have Professor Freedman tonight. She got her PhD in astronomy and astrophysics from the University of Toronto in 1984. She then was a fellow at the Carnegie Observatory in Pasadena and joined their faculty in 1987, became director there in 2003. She was chairman of the board of the giant Magellan telescope, which I'm sure she'll tell us about tonight, from 2003 to 2015. And now she's at the University of Chicago. She's a member of the National Academy of Sciences. She's a holder of the Gruber Prize in Cosmology, the Heinemann Prize in Astrophysics. And so with that, we're very, very honored to have Professor Freedman to give us a lecture tonight. Thank you.
Thank you very much for that very warm introduction and welcome. I'm delighted to be here this evening, and I am delighted to have met Ethel Miser and her son Harry and Bianca Fine. And it's a privilege for those of us who end up in physics and astrophysics and other areas of science. I think for those of us who love what we do, the opportunity to present our work to the public is something that I myself really am honored to have the opportunity to do. And more than that, we can't do science without the support of all of you, either through support by the government or support in institutes like this. And so on behalf of all scientists, I really do thank everyone, and particularly the Misel family and the Fine family, for your support. We could not do this without you. And I wanted to start this evening by asking you to think back. It's only been about 4 centuries. We believed at that time, 4 centuries ago, that the Earth was the center of the universe, and the sun revolved and all the planets revolved about the Earth. And it was Copernicus who told us in 1543 that in fact the Earth was not the center of the universe, the sun was the center of the universe, and all of the planets revolved around the sun. And in the early part of the 20th century, after having displaced the Earth from the center of the universe, we learned that the sun is not the center, but it's located about 2/3 of the way out from what appeared to be the center of the universe. And it was Edwin Hubble, and that name we now know because of the Hubble Space Telescope, who eventually was able to show that the Milky Way is one of many galaxies like our own, that are participating in an overall expansion of the universe. And as I'll describe, and as Professor Olive has alluded to, we've learned much more in recent decades, and the universe is continuing to reveal surprises to us. You have a much better version of this picture in your program, I realize, but I did want to thank the Misel family for this evening and the opportunity to be here. So if we are to learn about the universe in terms of what is actually the nature of the universe, the composition of the universe, the evolution of the universe, our tools in astrophysics are theory and also the use of astronomical telescopes. And it was Galileo Galilei in 1609 who first put a telescope and pointed it at the sky. He wasn't the first to invent the telescope, but he was the first to actually record what he saw and interpret what he saw and understand what he saw. And it is no exaggeration to say that every time we have built bigger and bigger telescopes, we have discovered something about the universe that we live in. And so this is a telescope in the Andes Mountains in Chile. It's a telescope, I believe I don't need this one. I'm going to move that there. It is a telescope that is located at an altitude of about 8,500 feet or so in the Andes. And why do we go to distant mountaintops? My grandmother used to ask me that question all the time. Why do you go to these remote places? And she was horrified when she learned there were no stores on the mountain. There's pretty much nothing on the mountain except for really sophisticated technology, large pieces of glass and steel that allow us to study the distant universe. And we go to these remote mountaintops for many reasons. One, the sky is dark at night. And for those of you who live in the city, and I grew up in Toronto, Canada, the kids growing up today, I think many have never seen a dark sky. And I was fortunate early on to have that opportunity and to be inspired eventually to go on and study the nature of the universe. It's also very dry in these dark mountains, and it turns out the air is very stable because it comes from the ocean without encountering any rough mountaintops on the way. And so it doesn't cause turbulence and degrade the resolution with which we can see. Here's a daytime view of the mountain. And when I started out in this field, as a graduate student traveling to the mountain for the first time, I was told that there was a woman behind every tree. So you can count the number of trees. and fortunately, I have seen that change over my career, and there are many more women who have entered the field, but it was very unusual at the time that I began. So what are the discoveries of the 20th century in cosmology? And the first and unexpected result was that by Edwin Hubble, who found that the universe is expanding. We don't live in a static universe. And as Professor Olive was alluding to, Einstein's equations allowed for either an expansion of the universe or a collapse of the universe, but not a universe that was static or stable. He forced it to be static by introducing what was a mathematical fudge factor. And then when the expansion had been discovered by Edwin Hubble, he later referred to it as his biggest blunder. But it turns out his introduction of this fudge factor, something we call the cosmological constant, may explain the third discovery here, which is that the universe is not only expanding over time, but it's speeding up, it's accelerating. And the second is that most of the matter in the universe turns out to be something that we cannot see. It emits no radiation, no light, no form of electromagnetic radiation. And we can only infer its presence by the effects, the gravitational interaction that we see as luminous objects or orbiting, say, in a galaxy, or motions in large clusters of galaxies. I'll describe more of that. But most of the matter in the universe is dark. It's not the stuff that you or I are made out of, or stars or planets or anything that we can see. And we don't yet understand the nature of the dark matter, and we don't yet understand what's causing the acceleration, something that we've termed dark energy. So if we go back to Hubble, this is the man Hubble. In 1929, he was observing objects that at that time were referred to as nebulae. And nebula is just a Latin word. It means fuzzy. And these were objects that had been discovered on photographic plates in the 1700s. They were cataloged. And there was a French astronomer by the name of Messier who was a comet hunter. And so every time he found a fuzzy object, he would label it with a number. And this is Messier 31. And throw it out. Wasn't of interest to him. These were the garbage objects because they weren't comets. And later turned out that many of the Messier objects are the galaxies that are like our Milky Way. And Edwin Hubble used the 100-inch telescope at Mount Wilson in California to make observations of stars in M31, and also known as the Andromeda Galaxy, and other nearby galaxies, and to infer the distances to them. We now have named the first orbiting optical space telescope in his honor, the Hubble Space Telescope. And what Hubble discovered is that there are myriad numbers of galaxies, and they come in various shapes and sizes. Some of them have spiral shapes. Our own Milky Way galaxy has these beautiful, very majestic-looking spiral arms. If we were to back off, if we could look at our galaxy from some distance face on, it would have a spiral shape, something like this. Galaxies merge with other galaxies, they collide. It's a dynamic and evolving universe, and that's something that we learned from Edwin Hubble's discovery. And I think it's no exaggeration to say that telescopes have changed our view of the universe. None of these three discoveries that I've just mentioned were predicted. They were observational discoveries. And we've learned much from the Hubble Space Telescope. And what's also interesting is that much of what it was imagined that the Hubble Space Telescope would do, it did, but it was the discoveries that we couldn't predict, that some of which have turned out to be the most interesting. And for example, we didn't know of the existence of dark energy at the time that the Hubble Space Telescope was conceived or was launched. We didn't know of the existence of planets outside of our own solar system. And the field has really changed in recent decades. So here are the Cepheid variables These are the stars that Edwin Hubble used to measure distances to galaxies, and these are the stars that we use today to make the most accurate measurements of distances to galaxies. And it is, if you do stop to think about it, a difficult thing to measure the distance to something that might be, in the case of the Andromeda galaxy, something like 2 million light years away. Now, what does that mean? We know that light travels at 186,000 miles per second. It's a constant speed. And so something that is 2 million light years away is the distance that it would take light traveling at 186,000 miles per second to reach us, traveling for 2 million years. And that's what we refer to in astronomy as the nearby universe. Makes sense, right? It really is astronomical, no exaggeration. Now, I only wish it were this simple that we would look at an image of a galaxy and see blinking stars and we would say, oh, there are the Cepheids. Turns out to be harder than that. These stars they're not unlike the sun, but they're more massive and they're more evolved. And maybe they're 5 to 20 times the mass of the sun, and they have outer envelopes that are actually in motion, they're pulsating. And the relationship between how fast they're pulsating, so this bright Cepheid here is pulsating more slowly than the less luminous, less massive, fainter Cepheids. And we can use this relationship, this unique relationship, plus the fact that as an object is further away, the luminosity, the brightness of the object dims with distance, and it does so in a very quantitative way. It falls off as the distance away squared. And we can make use of those properties to measure the distances to galaxies. But it wasn't until the launch of the Hubble Space Telescope that we could make these measurements very accurately for enough galaxies that we could solve this, what was at that time, factor of 2 discrepancy when the Hubble was launched. We didn't know whether the age of the universe was 10 or 20 billion years, or whether this Hubble constant, the rate of expansion discovered by Edwin Hubble, was 50 or 100. We now have other facilities. This is another sister telescope to Hubble. It's called the Spitzer Infrared Telescope, and we can make even more observations, accurate observations for some of the nearby galaxies. So one of the things we're able to do is overcome difficulties. For example, these stars are young stars. Stars form in regions where there's gas and dust that is collecting. It's held together by gravity. The stars collapse. Once they're formed, they're still near the regions of the gas and dust out of which they came. And the dust has a property that it dims, makes the stars look fainter, and therefore farther away. It also makes them look redder. And so techniques that, one of the techniques that I developed early on was to find a way to correct for this dust. And that's what we did with the Hubble Space Telescope. And we were able to essentially build up a distance ladder going from the nearby part of the universe out to more distant parts by tying in these distances from the Cepheid variables to other brighter objects, the supernovae. And I'll describe those more because we also use those for measuring the acceleration. And if you look at this particular plot, and I think this is the only plot that I will show you. I know some people in the audience are already cringing, saying, oh, do I have to pay attention to this? But bear with me, because it's actually a simple plot. It's what Hubble originally used to show the universe is expanding. And so this is the velocity increasing upward, and it's the distance to a galaxy increasing to the right. And what Hubble discovered, and this is his original 1929 plot where he announced that the universe was expanding, velocity, notice here, he has velocity in units of kilometers. Those of you who majored in physics here probably know that's incorrect. Those of you who didn't major in physics should know that's incorrect. Velocity is distance per time or kilometers per second. But this is what he actually published. It's in the National Academy of Sciences publication of 1929, got left off. And you can see there's a fair amount of scatter to the points here, but as the distance to the galaxy increases, the velocity, the speed at which the galaxy is moving away from us also increases. So there is this proportionality. The farther away a galaxy is, the faster it's moving away from us, and that's what led to the conclusion that coupled with Einstein's general theory of relativity, that the universe is undergoing an overall expansion. This small tick mark here, the first tick mark, is Hubble's, that's where Hubble's original data would fit. So we can now make observations out to much farther distances, and we can make measurements now that allow us to measure the Hubble constant, or the rate of expansion, to higher accuracy. So what we found was that the universe is 13.7 billion years old, so in the middle of this range, almost between 10 and 20 billion years. And the value of the Hubble constant that we got was 72. Together with, again, theory of general relativity, but other observations of the radiation that was left over after the Big Bang. So if the universe is expanding at the present time, then there must have been a time in the past when everything would have been closer together. Galaxies that we see today would have been closer together. And if you extrapolate backwards far enough, there would have been a time when the density of the universe was much higher, the temperature of the universe was much higher, and that's what gave rise to this theory we now call the Big Bang theory. Early time in the universe, tremendous explosion of all of space that has been expanding since that time. We only see the universe as it was when a fog lifted, and that is essentially the universe became cool enough that hydrogen atoms could form. There wasn't a dense plasma that had the radiation from the Big Bang being scattered in all directions, not able to get out. And we see the imprint of the early universe in the radiation from the Big Bang, and we can now measure very precisely small fluctuations in the temperature of that background radiation that give us very precise information about the amount of dark energy in the universe, the amount of dark matter in the universe, and other quantities that describe the overall evolution and nature of the universe. This piece here is meant to describe the universe in its earliest fraction of a second, and this is the remnants from the radiation about 380,000 years ago. And we now see galaxies today about 13.8 billion years later. So most of the universe is made up of matter that we can't see. It's dark. And we learned this early on. There was an astronomer at Caltech in the 1930s who was observing the motions of individual galaxies in a cluster called the Coma cluster. And the motions of the galaxies were so great that if all that we could see was all there was to the cluster, then those galaxies would have flown off long ago. They couldn't possibly be held on by the mass that we could see in the luminous matter. And no one knew what to do with that observation or that result. And so instead, it was effectively ignored for decades. And it wasn't until the measurement of stars within galaxies, their motions as they were orbiting about the centers of galaxies, as I'll show you in a moment, which also were too high to be bound to the galaxy, that people began to take this idea very seriously. There is matter out there we cannot see. We only infer its existence because of the gravitational interaction with, amongst the things that we do see in the luminous matter. In the 1980s, satellites were launched that allowed you to measure X-ray high temperature, for example, gas in clusters of galaxies. This gas is a temperature of about 100 million degrees. It would have evaporated long ago if there weren't more mass there holding it together than what we see in the luminous galaxies. Similarly, Einstein's theory predicted that you would have the bending of light in the presence of a massive object. If a distant source was traveling nearby, it would be bent distorted by the presence of the massive object. And we actually can see these arcs here. This is a Hubble Space Telescope image that, again, indicates that there's more matter there than we can see. So at this point, there are 7, maybe 8 different completely independent methods for measuring the amount of mass there is in the universe. And so even the most skeptical of astrophysicists who at the beginning thought there must be some fault in the logic or in the observations, it's inescapable now. There is more matter out there than we see in luminous matter. So what we're left with is here, if we look as observers, this is our view of the universe. We see these galaxies, clusters of galaxies, big walls and chains of galaxies. The universe is very lumpy, but the theorist's view of the universe is this is dark matter. Here's an actual image. And for decades now, we've been searching for evidence of the dark matter, or direct detection of the dark matter. There are many experiments in laboratories that are looking for perhaps very weak signals. Maybe the dark matter doesn't interact solely gravitationally, but it can rebound. These particles could rebound off the nuclei of atoms. And we look in accelerators for evidence of the dark matter. We look with gamma ray telescopes, for example, for perhaps particles that could be annihilating and give a signature of dark matter. But so far, nothing has been actually directly detected, so it remains a mystery. So what could the dark matter be? I remember describing to my 4-year-old son the dark matter one day. And I guess a few months earlier, I had been complaining about all the missing socks that go wandering around you can't find them in the dryer. And he said, maybe it's missing socks, Mom. And that one got ruled out pretty quickly. But what astrophysicists did for decades was to walk through a whole list of possibilities. What could this dark matter be? Well, maybe it's rocks out in space, or failed planets, or planets that just aren't orbiting stars. Maybe it's remnants of old stars, so stars that had burned out their nuclear fuel and were too faint to be seen. Maybe it's cold gas, and we see lots of regions where there is cold gas in our galaxy and other galaxies blocking out light from stars. Maybe it's hot gas in these clusters that I alluded to a moment ago. Maybe they're very compact objects and we just don't see them. Maybe they're black holes, and maybe they're dust particles, and we know there are dust particles out in the universe. And as many groups searched for the evidence of these possibilities, they were all ruled out. And this is further evidence that I alluded to. These are stars, motions. This is velocity again. And within a galaxy, as you go out in the galaxy, and I realize I do have another plot, so, but a similar theme here. So that the velocity here is too large to explain. If there were only the luminous matter that we see, this would be the behavior that we would expect. This is what we see, for example, in the solar system. As you go farther out in the solar system, the velocity is a function of position, and it's much too high. And hundreds of galaxies are now being observed. These are observations done by the astronomer Vera Rubin. And so what got left on the list is an as yet undiscovered particle, and perhaps a particle that was formed at the time of the Big Bang that interacts mainly gravitationally, but perhaps could have another weak type of interaction. And so Many groups have been searching for the evidence of this particle. A lot of work being done both theoretically here to understand the nature of the dark matter. And I would say at this time we're at an interesting junction. The limits have been strengthened considerably since people first began to realize that there was dark matter. But no one's found it yet. So I would say to the young people in the audience, if you think that everything's been done in this field, there's a Nobel Prize waiting for someone young out in the audience who will solve this problem. So the universe is not just expanding, as I said, it's accelerating. And we learned this because of the prediction that if we looked out in the universe, we kept measuring the expansion rate, we expected to see that the universe would slow down because of the presence of matter. That is, you would have the Big Bang, the universe is expanding, but all of the matter in the universe would tend to slow down that expansion, much in the way as if I threw, and I won't do that because I don't want to hit anybody in the front row, but if I threw this up because of gravity, this laser would come down. So no one was expecting, if I threw this up, that it would suddenly speed up and accelerate. And observations of these type 1A, we call them supernovae, and maybe I can just start this again so you can see it. These are objects that there's a companion, a very dense star, and an ordinary star that's its companion, and there's matter from the ordinary star that is dumping part of its matter onto this very dense star. Eventually, the star exceeds a certain mass and the star explodes, and it's such a luminous event that you can see it essentially across the visible universe. And so you can use these stars to measure the expansion rate as a function of time, because again, because of the finite speed of light, the farther back we look, the earlier we are seeing that light being emitted. And the surprising result was, no, the universe is not slowing down due to gravity, but it is actually speeding up. Turns out that a natural explanation for that is the cosmological constant that Einstein first proposed to stop the universe from expanding. Then when he realized that it was expanding after all, he'd lost the opportunity to predict it, he regretted and said it was his biggest blunder. And only if you're Einstein does your biggest blunder turn out to be something that explains the major constituent in the universe. The dark energy that is inferred from these observations of the acceleration contributes about 70% of the overall mass plus energy in the universe. The dark matter, or dark plus luminous matter, is about almost 30%. And stars contribute about 1%. So the luminous matter that we see is a tiny fraction. We really are simply observing the tip of the iceberg in terms of the composition of the universe. So when we go look for these supernovae, here's one right here. And again, they're simple to find because all we have to do is find the arrow, and it tells us where the supernova is. And so what we've learned is that the universe is accelerating. We think it's because of the presence of dark energy, some kind of tension, some kind of essentially a repulsive form of gravity that is allowed in Einstein's theory that's causing the universe to speed up. And it's been referred to as the biggest mystery in science. At this point, we don't have an explanation for the dark energy, resulted in a Nobel Prize in physics in 2011. But this is another homework problem for the 10-year-olds in the audience. And I hope someday someone out there in the audience who's interested in these questions in fundamental physics will be able to help solve, because they do remain at this point a mystery. So dark matter and dark energy comprise about 95% of the universe. The luminous matter is about 4% or so, and some of the ordinary matter, in fact, is not luminous, but it's the same kind of material that we're made out of. But at this point, we don't know the nature of about 95% of the universe. So, as I've described, much of what we have learned has come from observations using astronomical telescopes. So I wanted to turn for the last part of my talk to what we are doing, many of us, to build the next generation of telescopes. And for 12 years, I led a project, was the original chair of the board and president for what we call the Giant Magellan Telescope. This is a telescope that will be 80 feet in diameter, and there are 7 mirrors in this telescope. Each one of the mirrors is 27 feet in diameter. There are 6 mirrors that are in the outside and 1 mirror that's in the middle here. And the telescope will be built in the Andes Mountains in Chile. And just to give you some idea of scale, just to visualize this, so here's the mount of the telescope, and that's the Statue of Liberty. And the enclosure, I'll show you in a moment, I think here, yeah. So here, the enclosure stands 60 meters, or about 200 feet tall. It's the height of a 22-story building, but it's an unusual building because it has to rotate. And we have to be able to point the telescope to any direction in the sky where we're interested in observing an object. And we want to keep the temperature of the mirrors at the ambient temperature of the sky. So this is what we do. We fabricate these mirrors and throw them into the telescope, just like you see, and hope that they don't break. The first one actually now is leaving. I'll show you in a moment. We make them at the University of Arizona underneath the football stadium, and it's on its way south, the first of the mirrors, so that's an exciting milestone. These are actually based on engineering drawings. The lasers that you see here are what we use to correct for the motion of the Earth's atmosphere, something we don't have to do with Hubble, but which techniques now have been developed to allow us to actually correct for the blurring of the Earth's atmosphere, so we can get higher resolution than we can with Hubble for the first time. So this is the hole here, light, as I'll show you in a moment, comes through the central axis of the telescope and then down into the instruments where we can observe. So the GMT, the Giant Magellan Telescope, is going to have a sensitivity that's over 20 million times that of the human eye. If you were observing, say, from Madison, and this is something, so if you, I don't have any change on me, but if you were to hold a dime and resolve it from that distance using the GMT, you could actually read the print on the dime at that distance. And if you could light a candle on the moon, which you can't because there's no atmosphere, so you couldn't light a candle, but we would actually be able, it's sensitive enough that you could actually detect a candle on the moon. So what will we do with this telescope? One of the things that I think it will do, and again, what I find most interesting about a new capability is, my suspicion is we won't be able to predict what we will actually find. But the problems that we do know at the current time, we don't know how the first galaxies in the universe assembled. We can see the remnants of the Big Bang radiation and fluctuations in temperature and density that gave rise to the galaxies that we see today. They're the seeds of that. And we can use Hubble, and this is an image from Hubble, you can see these tiny little pinpoints of light, these very distant galaxies about which we have essentially no information, no resolution, and very low signal, and relative to the noise in the image. But what we will be able to do with the Giant Magellan Telescope is actually witness the galaxies forming for the first time and test our current theories, of which there are an abundance, of how this happens. We will be able to look at other planets. One thing that we've learned in the last couple of decades is that other planets and other planetary systems look nothing like the solar system. All of the models that have been developed for how our planet formed and other planets in the solar system turn out to just not be correct. And there are many different kinds of planets out there, very unlike what are in our own solar system. There is the possibility that with these giant telescopes we will actually determine if there is life elsewhere on other planets, that we will be able to detect that. All sorts of interesting objects, planet orbiting two stars. This was the first one that was discovered. For those of you who are Star Wars planets fans, you might remember Tatooine and the double sunset. But it's no longer science fiction. And so we don't yet have the capability, we don't have the sensitivity in existing telescopes or the resolution to measure masses of planets like the Earth, but that will become a real possibility with these large telescopes. So this is the football stadium at the University of Arizona, and many of us joke that future archaeologists are going to come back, they're going to unearth the stadium at University of Arizona and think, oh, this must be an important place. What did they do here? They made mirrors for giant telescopes. And so Roger Angel, who's the brainchild of this technology, was looking for space, and it turned out underneath the football stadium there was space, and he built this giant oven where these mirrors are fabricated in a process that puts in the original parabolic shape of the mirror that you need because of centrifugal force as the mirror is spinning, molten glass. And then if based on what had been done for the Palomar 200-inch, if you were to use the same technology for these mirrors, it would take about 60 years to grind out the glass and polish in the way that it was done for the 200-inch in the 1930s. So this spinning oven is where the mirrors are cast, and the technology to do this is new. These are off-axis mirrors. All 6 of the mirrors in the outer part have to focus light in a single place. And so the mirrors are polished to a precision that is equivalent to if you were to do the same polishing over the entire continental US. The height of the tallest mountain, if you could do that, smooth it out, would amount to 2 inches. So it's 20 millionth of an inch. These mirrors have been polished to a smoothness. That's what gives us 10 times the resolution of Hubble. If you have imperfections in the mirror, then it's going to send light in random directions. But if you can smooth them to that level of accuracy, we'll do 10 times better than Hubble. So if you look at, this is a nearby galaxy, and if you just, for example, look at these 4 larger blobs here, this is what we would see with our large telescopes currently on Earth. This is what we're going to see with the James Webb Space Telescope. This is a successor to the Hubble, and it's going to be launched in October 2018. So we will see much more detail than possible from the ground, and this is what we will see with the GMT. So it really is like putting on corrective lenses. Here we are again, and you can see why astronomers are eager to have this new capability. So we blasted the top of the mountain. This is what it looked like before we started. So this is another site where I showed you the original telescope early in the talk. It's now been leveled off, and this is an image from a drone taken recently. And there are actually dormitories that have been built down the side there, and so there's essentially a village now. There'll be 200 people who will be involved in the construction of the telescope, and that's expected to begin next year. So we just cast about to cast the 5th mirror next month, in fact, and we expect to have first light of the telescope in 2024. And this is just a vision of what it will look like on the mountain when it's constructed. It's quite a behemoth. So I think if we ask the question, how will we continue to learn about the nature of the universe and further understand its nature and its origin, there are many facilities that are on the drawing board for the next decade, and I think astronomical telescopes are going to continue to be a vital probe. This is the James Webb that I mentioned, this successor to Hubble. 18 independent mirrors are going to be launched and unfold in space. You can actually see this. It won't be serviceable like Hubble. It's got to work first time. We've been assured by the military that this is common technology and been done many times before, but I think you're going to find a lot of astronomers glued to their laptops and watching how this unfurls. There's also a satellite called WFIRST, and it's going to study the dark energy question, and that's due to be launched in 2024. So I think this remains an extremely exciting area, lots of questions that have been answered, lots of new discoveries that have revealed the nature of our universe over the last century, and I think the next century promises to be equally, if not more, exciting. So I thank you very much.
So we'll be happy to take some questions if there are some from the audience.
Just a couple there.
I've read, understand that maybe a way to describe the universe is that it has no edge. And I've always had some difficulty in trying to understand how that can be and to communicate that to the people I'm responsible to communicate that to, some of my astronomy students. And I'm wondering if you could help me out with that concept in any way.
Yeah. So everybody hear that at the back? Yeah. So I think it's a difficult concept, and I think part of the difficulty is that if we imagine something like the Big Bang, and you hear about an explosion, then we imagine it like an explosion, a bomb, and there's something in the center, and pieces fly off, and that there's sort of an edge to the universe that it's expanding into something, and it isn't the case. So what general relativity tells us is that all of space is expanding. Now that doesn't really help you understand that. So I think one way I find helpful to describe it and see if this helps you. So if we imagine, say, a ball and an ant, so a ball has a surface, a two-dimensional surface, right? And so if there's an ant crawling on the ball, then the ant can go anywhere on the surface, but there's no edge to that surface. It's not going to fall off. It's in two dimensions, there's no edge. And general relativity is a theory that has three spatial dimensions, one time dimension. So you can imagine an analogy that there's a four-dimensional universe. You're not visualizing that probably right now, but mathematically that's a good analogy, and there's no edge to that. So as the universe is expanding, space is being created. The whole universe is in new space is being created, and there's no edge to that. So I don't know if that helps you think about it. Well, so we don't understand yet enough about the nature of what the future evolution will be. And dark energy doesn't help us because we don't know what the dark energy is. So does the dark energy decay with time? Is it changing with time? Will we just expand indefinitely? And that was an easier question to answer when we thought there was only matter in the universe, because the universe is either going to collapse or it's going to, keep expanding. And that was simple. But the problem's no longer quite as simple.
Whatever happened to the concept that it was going to expand to a speed, it was going to gradually expand, but then all of a sudden, it was going to slow down, and it was going to reverse and start collapsing on itself. Whatever happened to that theory?
Yeah, so the idea was that it would expand, then gravity would take over, and you get a big crunch, and that maybe you could keep oscillating. And so a lot of the early debate, and so what people talked about in the 90s when we thought there was only matter, was that you could have enough matter, the density would be high enough that you would eventually stop the expansion and it would collapse. But now with the discovery of dark energy, it appears that the universe is going to keep expanding. Now, whether or not there are still some theories that allow for an oscillating universe, but there's no evidence for that. And as I said, we don't really yet understand what the dark energy is, so we can't really rule out that it won't have some property that it changes over time. But our observations now indicate the universe is accelerating, and it's likely to continue to do so.
May I ask a question? Question about the telescope, Magellan telescope. You built it in Chile, which is known to be pretty seismic. If an earthquake happens, what's going to happen to this telescope?
Yeah, no, a lot of effort is going into thinking about how to make it earthquake safe. It's been designed to withstand a 1 in 500 year frequency earthquake. But we build telescopes on mountaintops, same as true as Mount Wilson as the Andes, that they got thrust up somehow. And they're geologically areas that have a lot of earthquakes. So our current Magellan telescopes, we have them on a mount that allows the telescope and the foundation to shake, and if it's too much of an acceleration in a horizontal direction, it gets stopped. And there are earthquakes that happen all the time. We've never had one large enough that it created a lot of damage. I think the instruments are likely to get damaged. I didn't go into detail, but the shaking at the top of the telescope is really quite profound. So the secondary mirrors, I think, would be in danger. They're not as expensive. The primary mirrors, if all of them were to crack, that'd be a huge problem. But they're actually pretty rigid. It would have to be a very large quake to cause that kind of damage. But as I say, it's being designed to withstand a 1 in 500 year level earthquake. What's that? Yes, we would do that, but so the James Webb, we would love to have a 25-meter telescope in space. The James Webb is a 6.5-meter telescope. It's an $8.8 billion facility, and we don't know how to put a 25-meter in space. Yeah, someday.
Why is it that in the first three dimensions of space we can go backwards and forwards, but in time, the fourth dimension, as far as we know, we can go forwards, but we can't go backwards? Is there a chance that someday we will know how to go backwards in time?
We don't know how to do that now. And there are no physical laws that allow you to do that without violating some other physical law. Someone at the Fine Theoretical Institute want to take a stab at doing that?
Well, we describe nature. We can't say that we understand it on absolute first principles, but there is a real difference between time and the spatial dimensions. Technically, it involves, when we measure distances or times a minus sign. So there is something that distinguishes time from space. And in the spatial dimensions, we are allowed to move in any direction, but in the time direction, we're only allowed to move one way. It's a very, very fundamental question. All we know is that we try and describe what we see. We develop laws of nature, and the laws of nature that we develop explain the phenomena that we see. Those same laws prevent us from moving backwards in time. That's about as best as we can say.
G. Wells, when he wrote his time machine, and he could go forwards and backwards. As far as we know, currently, that's not
possible.
feasible. But, you know,
H.G. Wells was great, but he wrote science fiction, and the fiction part is really important. You know, I love science fiction as well, but there is a part of it that's fiction.
well,
Which
you know,
it's really helpful because it makes a lot of stories much more interesting.
well, science fiction has a way of becoming science fact.
Bianca?
Dr. Freedman.
Dr. Freedman.
Oh, excuse
second.
me.
Why don't you go, Bianca? why
Maybe
don't you
his
go
name
first?
is Bianca as well. He can go ahead.
Okay.
Okay.
Go ahead.
Dr. Freedman, there are dozens of questions I'd like to ask you, especially about the red giants that you're going to be talking about tomorrow. But I'm going to use this opportunity to give you and everyone here an invitation. I'm a member of the Minnesota Astronomical Society, and we've noticed over the years that many of our top professional astronomers are starlight deprived. They spend all of their time looking at screens. And so we've gotten to have a few of them out to our observatory. The Minnesota Astronomical Society has a couple of beautiful observatories out at Eagle Lake in Baylor Regional Park, not far from here. And this Saturday, we're celebrating Fall Astronomy Day. From the Eagle Lake Observatory, you can see the Milky Way. It's open and free to the public. If you looked for the Minnesota Astronomical Society on the internet, you would find us very easily and find maps and how to get there. The Astronomy Day is very nice. Our observatories are on a beautiful grassy knoll in an amazingly nice park. You're welcome to come out there. There would be untold numbers of people who would be happy to give you a ride. But it's just, so this Saturday.
Well, thank you, and I encourage anybody who can go to go, because those types of events they can be really exciting. What's that? I don't know. The mountain's a pretty magic place.
I had two questions from an ignorant person. You said that there is no edge to the expanding universe. But if one were to stop time and take one point in time, would then not the universe have an edge? And second question, where does the universe expand into?
So I don't know how to stop time, but I do know how to now look at what the universe is doing. And so we can measure now, when we measure the expansion rate, we can use Einstein's general relativity to integrate backwards and tell you how long the universe has been expanding for. And so we see essentially a visible edge. Maybe that helps you. That's the edge that's defined by how long the universe has been expanding for, and the speed of light, the finite speed of light. Now, of course, the universe has been expanding in the intervening time, so it's larger than just the light travel time and distance. But that, in a sense, defines an observable edge. And that's something that we can define. The universe is not expanding into anything. I mean, the universe is continuing to expand and to create new space as that expansion is going on. I don't know if you have a way that you can help. How do you?
There's your example with the ball, I think, is very good. You can maybe make it sharper by saying, suppose you just had a one-dimensional universe, which was a circle, and you had to be on the circle, so you can move both directions around the circle, clockwise or counterclockwise. There's no edge there. But the circle can get bigger, and now you have more room to move around in that circle. Now you're still thinking, well, but it's getting bigger on the plane. And then you go to the sphere is getting bigger, and so you have more area on the sphere, but it's getting bigger into something. But that something isn't physical. Now go one dimension higher, and you have the three-dimensional space, and it's getting bigger, there's more volume. But don't think about it going into something, because that's, again, just a construction to help us visualize it. Alternatively, the universe might be infinite, and then there's no edge anyway, because the universe just goes out forever. And it's filled with matter throughout the universe at some uniform density. We can only see so far, as Professor Freedman just said, because light takes a certain amount of time to get to us, and the universe is only so old. And so there's an edge, as she said, exactly, an observable edge, yet the universe is infinite, so there's no physical edge.
Thank you, and thank you for a lovely, lovely lecture, Dr. Freedman.
Thank you.
So I see a question out, oh, we have one here, and then we have a few still.
So if density equals mass divided by volume, and at a singularity there's zero volume, then that's dividing by zero, and that doesn't really exist. It's undefined. So how does that density exist?
Can you repeat that, maybe?
Okay, so at a singularity, there's no volume, and density equals mass divided by volume, and volume is in the denominator, and it would equal zero in this case, but dividing by zero is undefined, and that doesn't really exist, so to speak. So how does that density physically exist? Do you know?
You want me to?
If it doesn't mathematically exist.
So the key word is singularity, and at the singularity, all your bets are off. Now, we use that because, we like to make this whole nice picture that we understand the Big Bang and all of that. Well, we understand it up to a certain extent. There's a limit to our understanding, and that is the limit that we understand gravity. And there is a certain point, a certain density, so that we can understand densities that are extremely high, not infinitely high though. And so our theory is not complete, and the hope is, and here's another project for the 10-year-olds, the hope is that once you understand the theory of gravity at a much more fundamental level, that it would resolve that singularity, and there's not really a singularity there, and so that the density really isn't infinite, and maybe the volume isn't really zero. But you're pushing it to the point where we really don't understand it fully.
Yeah, so the laws of physics, so there are places where we can actually test the laws of physics, and it's surprising how high a density you can go to where that's true. But when you're probing the smallest scales in the early universe, as the Professor Olive says, all bets are off. The laws of physics, we don't know what the laws of physics are. And we don't yet know how to describe the quantum universe of the very small along with gravity. It doesn't make sense. It falls apart.
So there was a question here.
So I have a question more about the GMT than just about the universe in general. My question is, if the data from the GMT is going to be publicly available, how long will it be after it is operational?
So there will be an archive for the GMT, and there is a science working group that is trying to define what goes into the archive, when does it become available? And I would say roughly 1 year after the observations. So the scientists who propose the observations, who take the data, who spent a long time thinking about building the telescope, would have some period of proprietary access to do the science that they set out to do, and then it would become available to the public. Anybody who wants to have access.
Do we know anything about the distribution of dark matter in the universe? Is it equally distributed? Is it unequally? And if we know anything about it, what does it tell us?
Yeah, we do know a fair amount about the distribution of the dark matter, and it's clumped. And the distribution of ordinary matter, essentially, because it's interacting gravitationally with the dark matter, they tend to follow. So if you have a region where early in the universe the density is higher than another region of the universe that might be underdense, then you get gravity in the region that's denser pulling things together, and that increases over time. So you get a runaway effect where the denser, the rich get richer and the poor get poorer. The dense regions get more dense and the voids or the empty regions get more empty. And so the distribution of the dark matter is very lumpy. We don't know, again, because we don't know the nature of what the dark matter is. We don't know in detail how it's interacting with itself. So there may be some differences that we haven't yet been able to learn about, but overall, broadly speaking, it's a lumpy distribution just as the matter is.
Going back to the question about singularities and dividing by zero, is the same true for black holes?
Broadly speaking.
Probably. Again, if you make us give a definite statement about something we don't know, it can't be that definite. Black holes are typically shielded by what we call a horizon, and so that's the volume of the space around what we say is the singularity in which light can't escape from. So whether there's actually a point where the density is infinite or whether there's something smooth or something else going on, we don't know. Again, that same thing applies, that you need to have a theory of gravity which is beyond our current knowledge, and that really does mean having a theory which combines quantum mechanics and gravity.
Are there Cepheids in the Milky Way that are bright enough that you could see them with a relatively small telescope? Just curious.
Yes, there are, and you have to sort of define what you mean by small. But we have a 300 millimeter telescope at Las Campanas, and we certainly observe them. And also we observe another kind of variable star called auroral Lyrae stars, and we can observe those with a small telescope. So yes, the ones that are nearby in the Milky Way you could observe with a small telescope.
Hi, yeah, I'm here. So before it was said that you found that the space is flat, but is there any chance you allow some curvature in space? Because if you do allow some curvature, then it changes the, like maybe the distance between light is more than it would be on a flat universe. So are you allowing that?
Yeah, so the limits on that really have improved in recent years. And for example, with measurements of these tiny fluctuations in the temperature of the microwave background that I described briefly, you can measure now and put very stringent limits on the curvature. So whereas before, you really had to add a lot of data together to come up with, constrain that parameter of flatness. Now you're pretty much getting it from the microwave background observations plus maybe one other thing to put some constraint on it. And that's coming out at flatness almost identically. It's very hard to see how you would get out of that now. They're still proposed. There are, I didn't go into the new discrepancy that's arisen. So this difference in the Hubble constant between 68 and 73. No, if that's real, and we don't yet know if it's real or not, it could mean that there's some additional new physics. And so it could be that there's changing property of dark energy with time, some decaying dark matter, maybe another particle that's moving at relativistic speeds early in the universe, or there is curvature. But there's no good theory to explain that, and the observational evidence at present doesn't support that. It really appears to be a flat universe.
Hello. Thanks for the interesting lecture. I was just wondering, you mentioned right now that denser regions of the universe are getting even denser. So my question is, within solar systems or galaxies, between known planets, for example, Earth and Neptune, is the distance between planets and stars decreasing within dense regions, or is it increasing since the universe is expanding, for those that we can measure?
Yeah, so within our own solar system, dark matter and dark energy don't really affect things. Although people have been looking for signatures of dark matter, perhaps in the sun, maybe we can detect particles that are interacting that could be the dark matter. It's really when you get out to larger scales that you begin to feel the effects of the dark matter and the dark energy. So nearby galaxies, so we're talking about scales, we get out to the scale of what we call our local group of galaxies. So things like Andromeda that I mentioned early in the talk, it's another spiral galaxy like ours, and there are others in our own local group. And they're being held together by gravity, and the dark energy is not causing them to blow apart. The gravity is actually winning in that case in the local universe. So no, we don't see those effects nearby.
I think there's still a little backlog of questions, so maybe we'll take a few more.
I'm just wondering what your biggest challenge, research challenge, will be going forward.
Funding. And I'm not kidding. So technically, we know how to build the telescope. When we get these things going, analyzing the data, it's an ongoing challenge. It's the funding. And science has become more expensive. We've solved the easier problems, and now to make headway with some of these new problems require facilities that are larger, computing speeds that are faster, and that requires funding. So it's a serious issue.
So, question. Can you conjecture the results of this experiment? Say it's 2030 and I have access to the biggest telescope in Chile, and I point it out in this direction and see something recognizable, the Twin Peaks of Azerbaijan or something at the very edge of time, 13 some odd billion light years away. And then I turn the microscope, the telescope around in exactly the opposite direction. Would you expect me to be able to see the other side of that?
The answer is no. What you're referring to is that if the universe is closed, light in principle you would think could travel around. The universe has this funny built-in property that in a closed universe, that light emitted in one direction at the moment of the Big Bang. So a closed universe, again, without a cosmological constant would recollapse. Light emitted at the moment of the Big Bang traveling in one direction, it would take half the lifetime of the universe to get to the other side, and the other half of the lifetime of the universe to get back to the same point. So if you wanted to see the back of your head, right, so you shine a light at the back of your head and look that way, it would take the entire age of the universe to see it. So when the universe recollapses, if you shine that light at the birth of the universe, you'll see the back of your head right before the big crunch. I think one more question I think there's there. So
So my understanding is when we're talking about the curvature of the universe, we're talking about the curvature of 3D space. Do you have a analogy that, it's a hard concept to wrap my head around. Do you have an analogy that would help understand that, or are we back to the ant on the balloon analogy?
Well, in terms of the geometry, so if the universe is flat, which is what we're measuring, what that means is that the geometry of the universe is Euclidean, which you studied that in high school geometry, right? What it means is that the angles of a triangle add up to 180 degrees, and it means that if you have parallel lines, they will stay parallel. So there is a way to visualize that. And if we had a curved universe, if we had an open universe, one that would expand forever, then you'd have triangles that would have less, add up to angles at less than 180 degrees. And if it were a positively curved universe, it would add up to more. And so, yeah, I think there is an easy way to visualize that. We live in a universe described by the geometry that was originally described by Euclid.
Okay, I think with that, let's thank Professor Freedman again for his wonderful lecture.